of the rocket equation. What is the tyranny? If you have a rocket, its design hinges on a momentum balance that we call the rocket equation. And the rocket equation involves the magnitude of the gravity field that you are navigating in, which basically says where do you want to go. And you have to have propellant, right, because you got a rocket. And the propellant gets its energy from chemical bonds. So these two things that human beings have almost zero control over, the magnitude of gravity and the energy and chemical bonds, constitutes what I call the tyranny of the rocket equation, because it holds a strong grip on how we can make our rockets. Now, notice, I have the latest hipster computer-generated fonts. These fonts are crafted so skillfully on the computer, they mimic handwritten slides. Okay, so you have a rocket. You can see my little picture of a rocket. There's two things that are really, really important about the rocket. One, the rocket velocity. This is how fast your rocket is going to go. And then the exhaust velocity. That's how fast your propellant is going to squirt out the nozzle. And these two things, these two velocities, are inputs into this rocket equation, which is a momentum balance. And you turn the crank, and out from the rocket equation comes the mass percent of your rocket that has to be propellant. And you can't deviate from that, or your rocket won't get to where it's supposed to go. So what we're going to do is we're going to independently look at the rocket velocity, then we're going to independently look at the exhaust velocity. We'll plug them into the rocket equation and calculate what the mass percent of your rocket has to be. So where do you want to go? Well, we're going to start on Earth, so you are here, right? And I think we are all here, except for a few of the presenters that presented earlier today. They're already in space. But we are here, and you want to go someplace out there. Well, where is out there? There's orbit, there's the moon, there's Mars, there are places between the Earth and the moon. We call it the Earth-Moon cis space. And there's Lagrange points, there can be asteroids, there could be geostationary orbit. So pick where you want to go. Do your physics for navigating in that gravity field, and out comes your rocket velocity that you have to obtain or you won't get there. And I put some of those on there. To go from Earth to Earth orbit takes 8 kilometers per second. That's around 17,500 miles an hour. So you really got to go fast. Now, to get to moon takes 14. To get to Mars takes 16. So just think about this. Going from Earth surface to Earth orbit takes half, sometimes more than half, of the velocity required to go anywhere else you may want to go. So perhaps the giant leap for mankind was not the first step on the moon, but going from the surface of Earth into Earth orbit. Now, let's look at our choice for propellants. And this defines the exhaust velocity because the energy in the propellant comes from the chemical bonds and it goes squirting out the nozzle, so you got the velocity. And I've chosen a class of around 4 different kinds of propellants, ranging from solid rocket to kerosene oxygen hypergols. If you oxidize, you mix them together, they spontaneously combust. I had a friend of mine who he would always describe his latest relationship with his girlfriend as hypergolic. And then we have good old hydrogen oxygen, which turns out to be one of the more energetic chemical reactions we could use. And these are all chosen from real rockets that we could take real payload and real human beings into orbit right now. And there's the exhaust velocities. Read it and weep, because that's all you can get right now from chemistry. So let's take those now. Let's go from the surface of Earth into low Earth orbit, 8 kilometers per second. We're going to choose a variety of rocket propellants, plug them into the rocket equation. All the chalk dust is going to fall. And here is the result. Okay, look at that. Mass percent propellant. They're all around 90%. That means your rocket sitting on a launch pad, 90% of it is propellant, and 10% of it is everything you think of as the rocket. And that's dictated by this tyrannical equation called the rocket equation. Now, this is a pretty simplistic approach. It's almost a naive approach, something that you do as a freshman in physics class. But real rocket scientists, or really, I should say, rocket engineers, sharpen their pencils and let's see what real rockets can do. And there's the Saturn V, the Space Shuttle, and Soyuz. 3 working real rockets. Notice, 85 to 90% propellant for real rockets. That means 15 to 10% of everything else is the rocket. And part of that has to be the payload, which adds meaning to your mission. And so the payload that you could take in a rocket is around 2%. So 2% of everything you see on the rocket ends up being a freight that you can deliver FOB to orbit. Now, let's look at the implications to design. I mean, engineers have to design these things. And I've taken a couple classes of vehicles we're all used to. Let's look at surface vehicles. Okay, and I've taken the Queen Mary, my pickup truck, and a locomotive, and these things are all less than 10% propellant. They can have high payload capability. 60% of the mass of these things could be payload. And they're made out of billets of steel, and they're robust. Now, let's look at aviation, airplanes. 30 to 40% propellant, up to 40% payload capability. These are truly lightweight structures made out of aluminum, made out of epoxy graphite composite, sometimes titanium. You got to roll your engineering nickels around when you get to airplanes, and you just can't wantonly drill a hole through some part of the structure because you want to bolt on a new bracket or something like that. You got to do your engineering when you get into something that's 30 to 40% propellant. Now, look at rockets. They're not even in that category. 85% propellant, 2% payload. Rockets are on the edge of our engineering ability to even make and also pay for. And I put another category of devices. They're called explosive devices. And there's a Molotov cocktail. And so rockets are closer to explosive devices than they are any other kind of vehicle that we're used to traveling in. And if the energy involved in using a rocket gets released in any other way that it was designed, its result is similar to that of an explosive device. So now, we know where we're going. We've got our rocket built. A corollary question to the rocket equation is, what are you going to do once you get there? And gone are the days of going into space and coming back and saying, what a good boy am I. We have to go into space and we have to do something meaningful. And to do something meaningful means you got to bring payload. You got to bring something there, science equipment, whatever. You got to bring stuff with you, and that allows you to do a meaningful expedition. And so it got me thinking about the mass, because the mass of payload that you could take with a rocket is so vanishingly small. It's almost just the rocket itself because of the tyranny of the rocket equation. So I started to look at the mass that you could bring on a meaningful expedition, and I broke it into 2 kinds. Sophisticated mass. This is stuff like computers, life support, power generation, electronics, all this kind of stuff. And then there's mass that I call dumb mass. This stuff, air, water, propellant, cement, bricks, things that are needed by simply their bulk chemical composition or their physical properties. And then you look at a couple of different kinds of missions. You could look at exploration missions, sorties where you go someplace, come back. Or you could look at building an outpost where you cumulatively build new capability with time. And what you'll find is that it requires orders of magnitude, factors of 10 more dumb mass than sophisticated mass. So this might have some implications with the rocket equation. Now, when I was thinking about where to put the crew in this category, I wasn't quite sure which category the crew might go in. So this brings me to my final slide. The tyranny of the rocket equation. It involves the magnitude of gravity and the energy and chemical bonds which hold this tyrannical grip on our ability to even make rockets. And it's very difficult to even leave Earth, and it's particularly so to leave Earth with significant payload. If the magnitude of Earth's gravity were slightly larger, you could reach a point where we couldn't even get off the planet using rockets. So the question that I'd like to plant in all of you guys and gals' minds is something to do with rethinking rockets. Is there some other way to get off of Earth without using a rocket? Hence, you could break the tyranny of the rocket equation. Or, if we're not clever enough to think of an answer, and we have to use rockets, could we minimize the tyranny simply by we don't bring our dumb mass? Thank you.